as I said, I haven't really used Presenter before, so we'll see how this goes. Also, this is the first time that I've presented this particular work. I've talked about it with my advisors before, but this is new. So up until this point, just to give you a bit of background, what I've been working on was social network analysis with Whitman Richards. But then, once I'd handed in my master's thesis on social network analysis, I thought that I was ready to move on to something new. And also, I wanted to do something which was more in the classical vein of AI. And so it just so happened that a bunch of people were visiting Leslie's department, and also I was taking a course at Gambit, and so things sort of came together, and I ended up working on what was the continuation to the Dearth project. And so what I'm going to give is a presentation which hopefully will give my spin on what the core interesting problem, from an AI perspective specifically, about games like Dearth is, why it is stupendously hard, and then ways that we can get around the ridiculous hardness, what I've done to do this, and then some sense of where I'm at the moment with my research and where I would like to go next. But at the moment, as you'll see in the presentation, I've kind of reached a point where the easy things to do are done, and the hard things to do, it's not entirely clear which of them is the best. So what I'm looking for is, first of all, this is going to be my first time presenting this. Does what I say make sense? Is it appropriate for this kind of audience? I'm assuming that I'm not presenting to computer scientists. So I've made an special effort not to use any formalism at all. I'm trying to just give this in plain English terms and be as comprehensible as possible to somebody who hasn't come across this before. This is meant to be like an introductory lecture to my work. And then I also appreciate people, giving their feedback just without knowing a huge amount about the field as to what they think of the research paths that I lay out at the end would be most fruitful from the perspective of game studies rather than the perspective of artificial intelligence. Because there are two threads which I'm trying to weave together, and I have a good idea of what the AI problems that are interesting are. But that's not necessarily the same as what's interesting for games. All right, so let's go. So, first of all, we want to make an AI buddy that can help us out in video games. This is actually a more specific version of a general problem of just creating an AI buddy that can help us. And this is a well-studied problem which has been approached by a bunch of different people. Famously, there was this big, overarching, multi-university research project called Kalo, a collaborative assistant that learns and organizes. Fantastic amounts of money was spent on it, and a bunch of interesting stuff came out of it. So I believe that a whole bunch of user modeling stuff came out of that. Lots of natural language processing stuff came out of that. It was a real driver for AI research. But in the case of games, we have this kind of more specific requirement that, first of all, we need our AI buddy to be. I wonder if there's some way that I can make this. Let me just mess around with my power management settings. So in particular, computer games are real-time systems. They need to do all the processing that's required for AI between frame updates. Alternatively, they need to amortize the cost of doing all the planning for the artificial intelligence systems over several frames, but it needs to be done in a timely fashion. So the point is that a lot of AI techniques for doing planning and sort of working out what the best thing to do is, which we would need in order to make an AI buddy, are done in an offline setting. So you assume that you can do a lot of computation beforehand, and then you use the results of your computation to respond to things as they happen in the real world. But, hey, how's it going? So in the case of games, we may not have that luxury. And when I get through talking about Dearth, I'm going to point out some of the places where that general assumption is that we may have essentially infinite offline capacity for computation doesn't apply. So what people have done traditionally, I guess, or like the easiest approach to creating AI or efficient AI for games is to manually script behaviors for AIs. So the difference here is we could create a system which would reason about the world and work out what the best thing to do is, right? Or alternatively, we could define for any given situation that the agent is in, so that your buddy is in, what they ought to do. So that latter approach is manual scripting. The former approach is like this AI planning approach. And the benefits of taking a manual scripting approach is that you have like this strict control over the resources that the computer is going to use. So you can tailor it to the particular computational hardware that you're working with, and furthermore, you can perform tricks. So the point with part of the thing with game AI, right, is that you do not actually need a general purpose AI, a completely general purpose AI to play a game. Often all you want to do is create the illusion of intelligence, which is sufficient for the player to like be happy to go along with the story. However, when it comes to doing this manual scripting, there are some catches. First of all, actually doing the development is time consuming, so somebody has to sit down by hand, consider all the cases that the AI may need to respond to, and then code a response for them. There's often no reuse between games, so the AI that I write for Civilization is going to be different from the AI that I write for Modern Warfare 2. I mean, there's no common framework which can really be shared between the two of them. They can be hard to debug because there are these complex emergent behaviors between different scripted entities. And then the other thing is, you might just not know what the best thing to do in any given situation is. And you might not think of every given situation that your AI buddy could find itself in. So what do? You would like for your planning system to just consider all of these possibilities and have a plan, or be able to respond to them without you needing to manually say what the thing to do in this case is. So this is the kind of approach which Dearth took. That is, it took the model-based planning approach, where the AI planning system is responsible for considering all of these different cases, rather than the programmer who writes some kind of script which automates your AI buddy. All right. So, stepping back from games, we want to think about what the actual problem that we're trying to solve for an AI buddy is. What we really want is this thing which is called a policy. So a policy is like a black box which sits inside of your robot, and this is Leslie Kaeling's cute little robot which she uses for everything, which I've faithfully reproduced in Presenter. So it looks at the state of the world, usually using its sensors, like its digital sensors or what have you, or in the case of a computer, usually we'll have some summary of the game state, which will pass into the AI. And then it has this policy, which is basically a gigantic if-then statement, which says, if the world state is, I don't know, I'm standing in front of the table, then that my action should be pick up the chair. And for every possible world state that the agent could experience, there's an action corresponding. There's a corresponding action defined by the policy which it takes. So one way you might think about this as a policy being a function that takes world states and produces actions, or equivalently it might be a gigantic lookup table for which there's one entry, like a dictionary, for which there's one entry that contains the state of the world, and then you go down and find the state. So you find the state that you're in, you go down and look in your dictionary, and you look at the entry that gives you the action that you ought to perform, corresponds to that. Okay, so what I've described is like this exhaustive enumeration of all of the possible world states with an action corresponding to those things. So there are alternatives. And okay. And then the planning problem from an AI perspective, is generating one of these policies, like working out what the best thing to do in a given situation is. And an optimal policy is one which maximizes expected reward. So that is, it has some idea of what is good in the world, and then tries to behave in the way which will make sure that in the future, it will gain as much reward as possible, all things considered. So I just wanted to note quickly that there are alternatives to policies. You can act in the world without knowing what you would do in any given situation. So you might, for instance, just know what you might do in cases that you are likely to reach. So I don't need to know what I would do were I stranded on the moon. It's not likely that I'm going to end up in that sort of situation, so I don't need to waste space in my brain or time thinking to try and work out what I would do then in order to just do my everyday stuff. So we might think that policies, policies are like the standard way of thinking about what a plan ought to look like. So it's an exhaustive planning for every particular case that can come up, but we might imagine that there are cases where we don't need one of these. Okay, so before I talk about dearth, I'm going to talk about a different game which I've been using my framework to deal with. So this is basically a very similar setup to dearth. The specifics of it differ slightly, but it's easier to work with. So the thing about dearth is that, first of all, there's this kind of real-time element to it, which makes things a bit trickier. And it's, in a sense, not necessarily discrete. So you can sort of be halfway between squares in dearth. It's easier to think about things in terms of this sort of slightly simplified version that I'm going to be telling you about. So this is the example that I'm going to run with for most of the time. It's the ghost game. It's incredibly simple. You have yourself and your AI buddy. And the object of the game is for both of you to stand on a ghost. And the ghost that you want to stand on is just the ghost that the human wants to stand on. And that is all there is to the game. You can go, the actions you can take are go north, south, west, or east, or you can stand still. Anytime you take an action, it basically costs you a life point, or it has a cost to take it. There is a cost to taking action. So what you want to do in an optimal plan is work out how you can both stand on the ghost that the human is aiming for, but with both of you taking the minimal number of moves. Okay, so it turns out that this kind of game, and also dearth, and a very, very large class of other kinds of problems in a similar vein, can be modeled as this particular class of problems called Markov decision processes. And we're going to use this framework and way of thinking about how to model the world to set things up so that we can then apply some standard techniques from artificial intelligence to be able to solve these problems and come up with policies. So Markov decision process is made up of a bunch of different things, which I'll just run through quickly and give you a sense of what it consists of. So a Markov decision process, first of all, has a bunch of states of the world. These are ways of defining how the world can be set up. So this is an example of the state of the world in the ghost game. This guy's in the top left-hand corner. These guys are just all standing around. So specifically, for the ghost game, a state of the world is going to consist of a full configuration of each of these guys. So it's going to be like the XY coordinate of this guy, and the XY coordinate of this guy, and the XY coordinate of this guy, etc., etc. That is what one state of the world looks like. Then there are going to be actions. So, like I said before, the actions which are available to any of the agents in the Ghost game are move in each of the cardinal directions or stay put. So Markovian dynamics is a fancy way of saying what the next state of the world is only depends upon what the current state of the world is and what action you select during that state, in that state of the world. So the Ghost game is an example of one of these setups which have Markovian dynamics, because where we will end up, so where I will end up when I choose an action depends only on what state of the world is now and whether I choose to go like south or east, or what have you, whatever those actions that I choose. So non-Markovian systems I find actually kind of hard to think about, but the way to kind of get at what a non-Markovian dynamical system might look like is that where you end up in the next time step depends on like the whole history of everything that's ever happened in the universe in a really complex way that you can't summarize. So it's best not to think about non-Markovian dynamics because it makes problems real hard.
It's almost
and
like
not so
in
great.
Simov's foundation. That's how they calculated the future. That's really the example. It had a name, so maybe you can pick it up. See how close it is.
Psychohistory.
What? Psychohistory. Thank you.
Psychohistory, yeah. So next up, Markov decision process has rewards. So before I said that the object of the game is to stand on the ghost that the human is going for. The way that that works out as a reward in the Ghost game specifically is that you stop suffering the pain of existence once that happens. All right. So,
Thank God.
so the Ghost game is an incredibly bleak game. Every time you take an action, you feel withering pain. And the only thing that can give you sweet release from this horrible game in which you were trapped is standing on the ghost that the human is going for at the same time as the human is standing on it. All right, and finally, and any time you take an action which doesn't result in that state with you both being on top of the human, the human seeking, the ghost that the human is seeking, you kind of take a little pain. So the rewards are negative in this setting. And then finally, you have this last bit which is required for Markov decision processes, which is the initial state that you could be in at the start of time. And I was going to say something a little bit about discrete versus continuous Markov decision processes. All I'm going to say is the Ghost game is an example of a discrete Markov decision process, which means that we don't have to worry about the possibility of like being half in one square or half in another square. We don't have we model each person as just taking an action and then their action is fully resolved. It doesn't take time to do anything. Like when we advance time in the world, it happens in discrete chunks. And that makes things easier to compute. And that's also the way that Dearth is done. And then finally, there's this idea with Markov decision processes of temporal discounting. And the way to get at this is if we model the world, so if we just say that it's better to have good things sooner rather than later, then this idea is at the essence of, at the heart of temporal discounting. So by preferring good things to happen to me soon, what I'm saying, soon, rather than, so if I would prefer to have $5 tomorrow rather than $5 in 10 years, then that's an example of temporal discounting. And the reason that I'm mentioning this is because when I set up this model, I'm going to make use of this idea. So it's better to do things which are good now rather than do things which are good later.